MBA633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this segment, we'll work a problem involving hypothesis testing with two population means when the standard deviations of both populations are known. So the problem setting is the following. As part of environmental protection, an agency monitors the alkalinity level of a river at various points. The alkalinity in the upper reaches is known to be normally distributed with a standard deviation of 10 milligrams per liter, and that along the lower reaches of the river is 25 milligrams per liter. So we are told that the standard deviations of the two populations are known. Notice that in this case, the two populations that we're dealing with are the two extremes of the river, the upper and lower reaches. And so we want to compare the two the alkalinity levels in these two portions of the river. So a set of recent readings are taken from the upper and lower reaches, and the sample statistics that we get, one is the sample mean in the lower reaches yields 99 milligrams per liter alkalinity. The sample size is 15, and so 15 samples were taken in the lower reaches of the river. Similarly, 10 samples were taken in the upper reaches of the river, and we are told that the computed sample average for the upper reaches of the river is 80.5 milligrams. So based on what we see here in the two samples, the question is the following. At the 1% level of significance, is the average alkalinity in the lower reaches higher than that in the upper reaches? Once again, the 1% level of significance means I'm willing to accept a 1% chance of making the wrong call. The wrong call being rejecting the null when in fact it's true. So we're only checking for we're controlling for type 1 error. Okay, so to start off the problem, we'll have to set up our hypotheses. And remember the guideline that I stated. The guideline I stated is the way you construct the hypotheses is that you take whatever claim it is you're trying to establish and structure the hypothesis in such a way that that claim is the result of a rejection of the null, because that's what we do when we are checking for controlling for type 1 error. So the two parameters that I want to compare is the alkalinity in the lower reaches of the river, and I want to check if it's higher than the average alkalinity in the upper reaches of the river. So mu L and mu U. Mu L is the average alkalinity in the lower level of the river. Mu U is the average alkalinity in the upper reaches of the river. And I want to check if mu L is greater than mu U. And that is why I have set it up as the alternate, because that's the claim I want to establish. And if I am able to establish it, I want that to be the result of the rejection of the null. Okay, so that being said, whatever is left over is the null hypothesis, which is mu L less than or equal to mu U. Okay, so there we have our two hypotheses, and I can rewrite them very simply in this manner. Mu L minus mu U is less than or equal to 0. That's the null. And the alternate, of course, would be mu L minus mu U greater than 0. So just a restatement of the hypothesis that we had before. So obviously, since we are comparing two population means, the sample statistic that I would use to do the comparison is x bar L minus x bar U, the difference in the two sample means. That's the sample statistic I would use. And what do I get from the two samples? From the two samples I get x bar L minus x bar U is 18.5 milligrams per liter. Now if I just look at this difference, it seems to indicate to me that I should reject the null, because at least the result 18.5 milligrams per liter of difference seems to suggest that the null is not true. But of course, I won't be able to make a call on that for sure until I check whether the 18.5 milligrams per liter is large enough. And what do you mean by large enough? You know that process. We just have to standardize. And how do we go about standardizing? I need to know the standard deviation of the sample statistic that I'm using. Recall that all hypothesis testing starts with the assumption that the null is true as an equality. If the null is true as an equality, then of course mu L minus mu U would be equal to 0. That's what we have here. Therefore, the sample statistic, the sampling distribution of x bar L minus x bar U would be normal, of course, because the population is normal, and its mean would be 0, because that's what it would be if the null were true as an equality. And what would be the standard deviation of x bar L minus x bar U? We have calculated it, we have developed it in class. It's simply sigma squared L divided by NL plus sigma squared U divided by NU. So the expression here is pretty much the same that you had for a one population test case, except that there are two terms to be added together. So if you work through the math, you will find that the standard deviation of the sample statistic that we are using, which is the difference in the two sample means, it turns out to be 7.19 milligrams per liter. So as input, the 25 and the 10 that we used as inputs over here, these are given to us in the problem. So the standard deviation of the sample statistic is 7.19 milligrams per liter. Now I'm in a position to check numerically whether this 18.5 milligrams per liter difference is large enough. And you know the process, you simply standardize. So I want to check if 18.5 milligrams per liter is significantly different from 0. Why significantly different from 0? Because that's what we assume is true when the null is true as an equality. Okay, so divide by 7.19, and this turns out to be, let's see what we get here. Okay, so this would be equal to 18.5 divided by 7.19, which is 2.57, meaning this 18.5 milligrams per liter difference in the two sample is 2.57 standard deviations away from 0. Now, is that large enough? The only way we would know if this is large enough is if we compare it to our threshold of uncertainty. How much uncertainty am I willing to accept? Okay, so of making a type 1 error. So I'm willing to accept a 1% chance of making a type 1 error. What probability do I have with 2.57? So I just compute the probability of Z being greater than 2.57. So let me compute this number and then we'll give its physical interpretation. By the way, this value that we'll come up with, in order to get the probability of Z greater than 2.57, you know the routine. We will use the norm S dist function, but that will give us the area to the left of 2.57. So I have to do this 1 minus calisthenics here. So 1 minus norm S dist of 2.57. So before I hit return, notice that this whatever result comes out, this is the area to the right of 2.57. So it's 0.005. What is the physical interpretation of 0.005? It's as follows. What this is saying is, if the null is true as an equality, in other words, if mu L minus mu U is in fact 0, there is only a 0.5% chance that I would get a sample statistic at least as high as 18.5 milligrams per liter. Okay, highly unlikely to have occurred by chance. Since it is highly unlikely to have occurred by chance, my assumption must be wrong, so I end up rejecting the null. So mechanically, what do we have here? This is the p-value. Since p is less than alpha, I reject the null. Final conclusion, if I am willing to accept a 1% chance of making a type 1 error, I will conclude that the average alkalinity level in the lower reaches of the river is in fact higher than the average alkalinity level in the upper reaches of the river. The method that we have just used here is the p-value method. If you use the critical value method, you would end up with the same result, except that it would have to compute the critical value. So what would be the critical value? You remember the physical interpretation of the critical value. You obtain it based on your level of significance. If I'm willing to accept a 1% chance of making a type 1 error, how far away do I have to be from the middle, from the mean, in order for me to say that the sample statistic is extreme. And the way I would do that is I want a position on the x-axis, so I would use norm S inverse of 1 minus 0.01. Why 1 minus 0.01? Because you know that the norm S inverse function works with the left side area, so this 1% is the right side tail, since we have a right-sided test over here. So let's see what this gives us. Norm S inverse of 1 minus 0.01, and that ends up being 2.32. Physical interpretation of the 2.32, what it's saying is, if I'm willing to accept a 1% chance of making a type 1 error, then any sample statistic that is at least 2.32 standard deviations above the mean, I will consider it extreme enough and say that, hey, it's highly unlikely to have occurred by chance. And what did I actually find from my sample? From my sample, I found that the sample statistic, the 18.5 milligrams per liter, is in fact 2.57 standard deviations above the mean. It's above our critical value. So it meets my threshold of how far away it needs to be in order for me to say, hey, it's large enough, it's different enough from zero. So numerically, what do I have here? I'm running out of real estate a little bit here, so let me see if I can squeeze this in. I have here that Z is greater than Z critical. Okay, so the 2.57 is greater than the 2.32, so I still end up rejecting the null. Same conclusion. So my final conclusion, whether I use the critical value method or the p-value method, is that the average alkalinity level in the lower reaches of the river is in fact higher than the average alkalinity level in the upper reaches of this river.